All right, we are going to talk about residual plots and creating residual plots. Here's our example we're going to work through. We're going to do this both on paper and on Desmos, so you can see how to do it from both perspectives. So we're going to use this example. This is our scatter plot data we'll be using. Feel free to pause the video and write this down in your notebooks if you want to follow along. Also, this is the graph of our data. Again, you can pause the video and graph the data before moving on. Now, if you're doing this by hand and showing your work by hand, I will give you the line of best fit. Okay, you can also find this on Desmos. We saw how to do that in 8.4. Okay, so we have drawn both the line of best fit and our data points on the graph. All right, so residual plots are kind of the extra. What is the difference between the line of best fit and our data values? How to find that is by doing the actual, and these are all y values, the actual y value, which is the y value of your data, so that's this column here, minus the expected value. That's where you plug x into the line of best fit, and we subtract the y value of that from the actual y value. Okay, again, this is our line of best fit, so this is what we'll be using for our data. So here's how this works. And also on your graph, what that looks like is it's the vertical line. If you were to draw a vertical line between the data point to the line of best fit. Now, if your value is below the line of best fit, these two are going to have negative values. If it's above, it's going to have positive values. Okay, and when we're all done, our residual values should add up to 1. So sometimes you can count the distance. That's the same as what we're doing here. All right, so here's how to do this. Residual value is the actual. So for 1, the actual value is 10 minus the expected value. So what we're going to do is we're going to take our equation and plug in 1 because x is 1. So 3 times 1 plus 6. So 3 times 1 plus 6 is 9. So 10 minus 9 is going to be 1. So our residual value is 1. So at 1, if you take a look, because I'm going by 2's here, this is hitting halfway between 10 and 8. So that's at 9, and our value is at 10. So 10 minus 9 is 1. So that's our residual value there. Okay, let's do it for when x equals 2. So our y value is currently 13 minus, and let's plug it in. 3 times 2 plus 6. So 3 times 2 plus 6 is going to be 12. So 13 minus 12 also equals 1. And again, that makes sense there. All right, let's do the next one. 7. 7 minus 3 times 3 plus 6. That's going to be 15. This is going to be a negative 1. So 7 minus 15 is equal to negative 8. Now that makes sense. This has a much bigger distance. That has a distance of 8. All right, let's do the next one, number 4. We have 22 minus 3 times 4 plus 6. 3 times 4 plus 6 is 18. And 22 minus 18 is 4. That's this one here. That makes sense. That's also 4 units. Okay. 28 minus 3 times 5 plus 6. 3 times 5 plus 6 is 21. So 28 minus 21 is 7. That's this value here. That makes sense. That looks like that's 7 units. Finally, the last one, 19 minus 3 times 6 plus 6. That's 19 minus, this is 24. And that's going to equal negative 5. And again, that makes sense here. Those units are negative 5. Okay? So these are the residual values. Okay, and what we're going to do is now we're going to plot them. So these are the residual values. Now this is the residual plot, and you can plot them all in the same plot here. So 1, we're going to plot 1. Again, my y's are going by 2's. 2 is also 1. 3 is negative 8. So 2, 4, 6, 8. I'll have to extend my graph down a little bit. Negative 2, negative 4, negative 6, negative 8. That's about as far as I need to go. So down there. 4, my residual value is 4, so 2, 4. 5, my residual value is 7, 2, 4, 6 and a half, 7. And then 6 is negative 5, so 2, 4 and then a half, negative 5. Okay, so a couple things you should notice about this. Generally speaking, for residual plots, the x-axis becomes the line of best fit. So this really shows the differences between the line of best fit and the points. The closer they are gapped towards the x-axis, the better and closer the values are to the line of best fit. If they're all on here, that means you have a correlation coefficient of 1 or negative 1. You should have almost an even amount on top and the bottom. Now, if you notice, these values are relatively small and these values are relatively large on the bottom. So that's why we have more positive values than we do negative values. But overall, it should be an even number. So that's why this is a little bit off. Also, when you add up all of these residual values, they should equal 1, which these do. So if you add all these up, 1 plus 1 plus negative 8 plus 4 plus 7 plus negative 5, you should get 0. Okay, so that's another way to show that you're correct. So this is just another way to analyze how to draw your line of, or how to analyze your line of best fit in your data. All right, let's go to Desmos. Here's the same exact data. So hopefully this looks exactly the same. So this is a little bit faster. So we're going to do the same thing we did finding our correlation coefficient. So y1 squiggle mx 1 plus b. And what you might notice, again, we got our correlation coefficient, our 3 and our 6, right? Remember our equation is y equals 3 plus 6. Notice it says residuals. Let's go ahead and press that plot button. Notice what happens. Okay, couple things happen. You got this E1 column here. Those are our residual values that should match our table. Also, notice it plot our residual plot. So this looks identical to what we just did by hand. Okay, so that's 2 ways to do it. You can do it by hand, finding the actual minus the expected values, or you can do it by Desmos, which does it all for you. And that's how you deal with residual plots. It's the extra value between the line of best fit and the data point.